Hey, today I'm going to be talking about the superposition principle. This is yet another incredibly useful circuit analysis and design technique. It's something that will allow you to break a circuit apart into smaller pieces and make the analysis more palatable. And it's something that will help you understand what's really going on when we feed signals into our circuits, when voltages and currents interact with each other. Now there's a few conditions that have to apply, and I'll talk about those in 1 second. So let me write out the definition of the superposition principle. It states that a circuit's total response is the sum of its responses to the independent sources acting individually. And this holds if all circuit elements can be described by linear equations, and this includes the dependent sources in the circuit. What is a response? This is a word you're going to hear all the time when dealing with circuits. We call it a response because all of the things we're interested in measuring, i.e. voltages and currents, are the result of some source, some other place in the circuit. And this is true whether or not we're talking about DC or AC, whether it's a power system or a communication system. You better get familiar with this word response because it's used all the time. What does it mean that the independent sources are acting individually? So what we're going to do here is wind up zeroing different independent sources and looking at the effect that just a single source has on the circuit at one time, and then effectively add them all up at the end. And we'll find that the whole is equal to the sum of the parts. And the main caveat here is that every circuit element has to be describable by a linear equation, and this includes dependent sources in the circuit. It might not be entirely obvious what's meant by the word linear. A lot of times that can be very vague or general. It also depends on whether or not you're defining it in the engineering sense or the mathematical sense. And I feel like a lot of times people use the word linear and they don't really know what they're talking about. Other people don't really know what they're talking about. I'll try and give kind of a loose or rough definition in a later video that is by no means mathematically rigorous, but will suffice for now. Okay, I'm going to jump straight into a circuit example. What I've drawn up here is a circuit that has two independent sources and a single dependent source. Two resistors, R1 and R2. I have a voltage here, Vx, across R2, which I'm going to say is the total response that I want to measure. There's a current Ix flowing through R2, which controls this dependent source, modified by the constant K. So it doesn't really matter what K is. We're just going to leave it general for now and know that it's some constant number. So the way that I would go about solving for Vx is by using KCL at this top node up here. That's a good start. Let me go ahead and write that out. This is a KCL equation that describes the current flow at this top node, and I've also added that we know the current Ix by Ohm's law, Vx over R2. With that being said, we're going to substitute this into our original equation such that we can isolate Vx, thus giving us the total response, the total voltage on R2 as a function of the other circuit elements and the sources. So let me go ahead and step through that algebra. And here we go. I've gone ahead and substituted in our current Ix and isolated for Vx, which is the total response we wanted to measure. So here I have Vx equals a function of the resistors R1 and R2, the gain factor K, and our sources Vs and Is. Now I could have written this in a slightly different form, but I chose to do it this way because it will make our final answer more obvious. Now to be clear, what I've done here is completely correct, and this is what I've taught you to do in past videos. You've used KCL or some sort of nodal analysis to solve for some unknown quantity in the circuit that you wanted. This is everything that we've done before, and this is everything we'll continue to do. So I haven't actually shown anything new yet. What I'm going to illustrate is that there's a different way you can arrive at the solution, and according to the principle of superposition, it will match this answer. So let me go ahead and draw up another circuit that's a variation of this one with one of the sources zeroed. Here I have a variation on the circuit with one of the sources zeroed. I've chosen Vs. Notice here the only valid choices are independent sources. So there's going to be two subvariant circuits, one where Vs is zeroed and one where Is is zeroed. Kix, the dependent current source, will exist in both cases. So I've zeroed Vs and I've changed our nomenclature a little bit. I'm calling the voltage across R2 V1 because I'm counting up independent responses to sum via superposition for the total response. So for this first subvariant, I'm just going to call it V1, and in the next circuit I'll call it V2. So I'm going to solve for V1 in pretty much the same way that I did in the last example. We're going to do a KCL at this top node. Notice that things look incredibly similar here to our original case. It's just that the term involving the source voltage in R1 has changed slightly. So now I'm going to do the same thing that I did before and just substitute in our expression for Ix and isolate, hoping to find V1, which will be one element of our total response. And notice what we have here. If you solve this out, you'll get V1 equals R1 R2 divided by R2 plus R1 times K plus 1, and the whole thing multiplied by Is. So now I'm going to go ahead and draw up the last variant circuit that zeroes Is instead of Vs, and I'm going to measure the individual response V2 across R2. And then at the end we're going to sum that up with V1 and see if it's the same as the total response. Notice the difference here. We have Vs in place, except now Is is zeroed. And when you zero a current source, it means setting the current to 0 for all cases, which is equivalent to just creating an open circuit. So you can see how Is is now missing, Vs has reappeared, and yet again we're going to do the same KCL at this top node. And of course we already know Ix by Ohm's law, it's just that we have V2 instead of V1. So go ahead and write that Ix equals V2 over R2 and then substitute that into this equation. Then you're going to isolate for V2 the same way we did for V1, and hopefully find something that looks like this. So let me go ahead and do that. If you did your algebra correctly, you'll get something like this. R2 over R2 plus R1 times K plus 1 in parentheses times Vs. And this is fantastic because we can see pretty clearly, if you look back at our work on the previous page, that Vx, or the total response, is equal to the sum of the individual responses V1 and V2. This is a verification of the superposition principle. It tells us that when we analyze circuits, we can make our lives easier by looking at these individual responses instead of solving the entire circuit at once. And it also gives a little bit of insight into what's really happening, how these voltages and currents interact with each other in a linear circuit like this. Really, all the principle of superposition is an extension of the concept of linearity, or a linear system. And this is something that we'll deal with a lot in electrical engineering. We want our systems to be linear, and even when they're not, we'll pretend that they are. And you'll understand what I mean later. So anyway, I hope this was helpful, and I think I might do a brief video on elbow grease type linearity. So let me know if you have any questions, and have a great day.